All right, before we get into lesson number 9, I just want to talk to you about some non-permissible values. What we know is when we're dealing with any kind of equations, if there is something in the denominator, well, not something, a variable in the denominator, we know that we cannot divide by 0, so therefore the denominator can equal 0. Well, the same thing happens when we're dealing with trig. So let's say, for example, I have a fraction where sine of x is in the denominator. I know that sine of x cannot equal 0. But when I deal with non-permissible values, I have to deal with the variable. So it can't be sine x. We have to actually solve this for x. Well, let's take a look at the unit circle. And I'm just going to do the corners here. And I'm going to take a look, where is sine x equal to 0 on the unit circle? Well, we know that sine x is equal to the y-coordinate on the unit circle. So if I take a look, I know that that happens here, and it happens here. And when I deal with non-permissible values, it has to be absolutely every angle that could ever create a 0 for the y-coordinate. So I have to write that as a general solution. So if I have sine in the denominator, I know that x cannot equal to pi times n, where n is an integer. Because what that would mean is, let's say n is equal to 1. That would take care of this angle. And then if we keep adding multiples of pi, we would get all of the angles that land either here or here. So let's go back to the lesson. So what we're going to be dealing with today is identities. So what is an identity? It's an equation that's true for all permissible values of the variable in an expression on both sides of the equation. In other words, when the expressions on either side of the equal sign are evaluated for any permissible value, the resulting values are equal. Trig identities can be verified both numerically and graphically. So let's take a little deeper look into what non-permissible values are. So case 1, and that's the one I just talked about, where sine of x ends up in the denominator somewhere. So on the unit circle, I will grab one here real quick. On the unit circle, we determined that sine x is equal to 0 both here and here. So in radians, it would be 0, pi, 2 pi, or in degrees, it would be 0 degrees, 180 degrees, or 360 degrees. So the general solution would look like pi times n. Actually, we should put an x cannot equal, or x cannot equal 180 times n. Now what happens if cos is in the denominator? Well, if cos is in the denominator, we know that cos x, cannot equal 0. So where would x equal 0 on the unit circle? Well, we know that cos is equal to the x coordinate on the unit circle. So that would be here, and that would be here. So in radians, it would be pi over 2 and 3 pi over 2. And in degrees, that would be 90 degrees and 180 degrees. So let's take a look at the general solution there. X cannot equal pi over 2 plus pi n, where x cannot equal to 90 degrees plus 180 degrees times n. Okay, we're not going to worry about this stuff here. We're just going to talk about where would tan or cotan, if it appears in the numerator position. If you remember, back to the unit circle, tan and cotangent can be undefined on the unit circle. And let's figure out where that happens. We know that tan is equal to y over x. We cannot have an x value at 0. So, where does x equal 0? Well, we figured that out. So x cannot equal to pi over 2 or 3 pi over 2. So that ends up the same as case 2. That ends up as the same restrictions as cosine, right above here. So if we write that down, that would be, so for tan of x, that would be x cannot equal to pi over 2 plus pi n, or x cannot equal to 90 degrees plus 180 n. Now for cotangent, I'm just going to do that up here. We know that cotan is equal to x over y. So on the unit circle, we look at where y is equal to 0, and that's 180 degrees and 0 degrees, or pi and 0 and 2 pi. So my restriction here is x cannot equal to, and it's the same as sine, so pi n, and x cannot equal to 180 degrees n nei. So basically, whether or not tan or cotan, even if they're in the numerator position, they still have restrictions because there would be division by 0. And we're not going to put tan or cotan in the denominator, so don't worry about that. We're just going to worry about tan and cotan if they end up in the numerator. Case 4, that's if you have secant or cosecant in the numerator position. So we know that cosecant is equal to 1 over sine x, so it ends up with the same restrictions as case 1. Sorry, that was cosecant, so sine x is in the denominator, and they would have the same restrictions as case 1, which is x cannot equal to pi n, and you could do that in degrees. And then if we have sec x, cos appears in the denominator, and it would be the same restrictions as case 2, which is cannot equal to pi over 2 plus pi n. All right. Class example 1. I changed this one a little bit to make it a little bit easier. Determine the non-permissible values in degrees for the expression. So first thing I got to check for is what's in the denominator and deal with that. So I see cos x in the denominator, so I know that cos x cannot equal to 0. And then again, I solve it using the unit circle, so I know that x cannot equal to pi over 2 that's right, plus pi n. N is an element of integers. But I also have a tan x here. Whenever you see tan x, we know that tan, we have to deal with where is tan undefined. Well, because tan is equal to y over x on the unit circle, we've got to state the restrictions for where x is equal to 0. And that is the exact same as cos, so I've already dealt with that restriction here. So we only have one restriction. All right, verify an identity numerically and graphically. I just want to discuss a little bit the difference between verify and prove. They are very different words. Verify is actually, if we do it numerically, we just put an angle in there. If we do it graphically, we graph one side of the equation into y1 and the other side of the equation into y2, and we check to see that the graphs overlap. All right, so let's look at this question here. Given the equation, determine the non-permissible values. All right, first thing I'm going to deal with is sec. We know sec theta is equal to 1 over cos theta. Therefore, I have to state restrictions for cos theta. So I know cos theta cannot equal 0. Therefore, theta cannot equal to pi over 2 plus pi n being an integer. Now I'm going to deal with sine in the denominator. I know that sine theta cannot equal 0. Therefore, theta cannot equal pi n being an integer. And I also have tan. And we know on the unit circle, tan is equal to y over x. We know that can equal 0, but it's going to give us the exact same restrictions as here. So my restrictions are done by indicating both of those. All right. Now we are asked to verify. Whenever we ask for a verification, we will give you the angle that we want you to verify. And they are asking us to verify both a 60-degree angle and a pi over 4 angle. So here's the process. I write down the identity they give me, which is sec theta is equal to tan theta over sine theta. When I verify, I simply sub in the angle. So actually, if I'm going to use the unit circle, I'm going to turn this into 1 over cos theta. And now I'm going to sub in the angle. So I know this is 1 over 60 degrees is equal to tan of 60 degrees over sine of 60 degrees. All right, now we look at the unit circle. I'll just grab it again here quick. And we determined that cos of 60 is equal to 1/2. So this is 1 over 1/2, which simplifies to 2. Tan of 60 is equal to y over x. So if you simplify that, that is equal to root 3. And sine of 60 is equal to root 3 over 2. And once we simplify all of that, we determine that it is also equal to 2. So I have verified my identity by stating that 2 is equal to 2. All right, let's take a look at pi over 4. So again, I'm going to take the equation sec theta is equal to tan theta over sine theta. And I can never cross the equal sign here. I always make sure I do my calculations on the left, my calculations on the right, and make sure they're equal. So this is 1 over cos theta. So I have 1 over cos pi over 4. And here I have tan pi over 4 over sine of pi over 4. All right, cos of pi over 4. bring this up a little bit. So cos of pi over 4 is root 2 over 2. So I end up with 1 over root 2 over 2. Tan of pi over 4 is y over x, which simplifies to 1. And sine of pi over 4 is equal to my y value, which is root 2 over 2. So, to simplify this, it's 2 over root 2, and to simplify this, it's 2 over root 2. And if it doesn't ask you to rationalize the denominator, you don't have to. But it might ask you to, so if you did, that would be multiplying top and bottom by root 2, which would be 2 root 2 over 2, which would just be root 2. All right, use technology to graphically decide whether the equation would be an identity. Basically what we do is in y1, we put the left side. Since I can't put secant into my calculator, I'm going to put secant in as 1 over cos x. And in y2, I'm going to put tan over sine. Now, what you're going to do is you can, good Windows, you can use your 0 as your max, or sorry, min for x, 2 pi as your max, and then maybe go pi over 6, and just adjust the y window settings so you could see it, and the two graphs should overlap. So I'll let you do that and check that out, see if that worked out for you.